Welcome students for today's live session. Now I am going to discuss JEE mains question paper based on the topics electromagnetic induction, AC, moving charges and magnetism and matter. So these chapters are important chapters for JEE mains level examination. Out of all these, the questions based on electromagnetic induction are very much plays vital role in JEE advanced level examination also. So first we have to explain, we have to go and cover the points and ideas relates to JEE mains level questions based upon the following question paper I am going to explain now. Right, first question. A compass needle is free to rotate in horizontal plane. Its magnetic moment is 60 ampere meter square. When it is pointing geographical north, it experiences a torque of 1.2 into 10 to the power minus 3 Newton meter due Earth's magnetic field. If Earth's magnetic field in horizontal direction is 40 into 10 power minus 6 Tesla, what is the declination at that point? See here, the compass needle is free to rotate in horizontal plane and its magnetic moment is given as m equal to 60 ampere meter square. When it is pointing towards geographic north, it experiences a torque. So torque acting on a bar magnet is 1.2 into 10 to the power minus 3 Newton meter. Here magnetic needle or compass needle is treated as a bar magnet of magnetic moment 60 ampere meter square. So when it is placed in the external magnetic field, that is in Earth's magnetic field, that is horizontal component of Earth's magnetic field is given as 40 into 10 power minus 6 Tesla. Then what we want? What is the declination at that place? So the torque experienced by a bar magnet placed in the direction in a magnetic field, then the torque is represented by the equation T equal to mb sin theta. So this theta is the declination at that place. Therefore sin theta is equal to torque by mb. Instead of mb I write mbh because horizontal component of Earth's magnetic field is given in the data. Therefore sin theta is equal to torque by mbh. So torque value is given as, what is torque value here? 1.2 into 10 power minus 3 divided by magnetic moment is 60 into BH value is given as here 40 into 10 power minus 6. So after calculation we get sin theta value as, here it is 1 by 2. So do the calculation. After calculation we get this value as 1 by 2. So sin theta is 1 by 2 means theta equal to 30 degree. So declination at that point is, at that place is equal to 30 degrees is the answer for question number 1. So for question number 1 answer is C. So simple question it is, but try to understand here what is the torque experienced by a magnetic needle kept in the external magnetic field, nothing but here horizontal component of Earth's magnetic field, that is tau equal to mb sin theta. In place of b it is replaced by bh. Here theta is called here angle of declination at that point. So that theta to be calculated, that gives your answer. So answer is C for question number 1. Question number 2. An LC circuit consists of a capacitor and a coil with a large number of turns. Suppose all the linear dimensions of all elements of the circuit are increased by a factor. Linear dimensions of all elements of the circuit are increased by a factor 2, while keeping the number of turns in the coil remains constant. Then how does the resonant frequency of the circuit will change? So what is the resonant frequency? F equal to 1 by 2 pi into root of LC is the equation for resonant frequency of LC oscillating circuit. So we know that the equations are for self inductance of the coil, mu naught into n square AL. Mu naught into n square AL, and also the capacitance value in terms of linear dimension C equal to epsilon naught A by D, that equal to epsilon naught into L into breadth, length into breadth by D. So these are the equations for self-inductance of the coil and capacitance of the coil. See the data. According to given data, all linear dimensions. What are linear dimensions here? Length, breadth, and also the distance between the plates of the capacitor. All are increased by a factor 2. All are increased by a factor 2 while keeping number of turns remains same. So therefore, F value is equal to 1 by 2 pi into square root of 1 by 2 pi into square root of mu naught into, in place of n it is n square by L square into L gets cancelled, n square by L into A, into capacitance epsilon naught into length into breadth by distance between the plates of the capacitor. Here L increases by 2 times and B increases by 2 times and D increases by 2 times. All increases by 2 times. So here n kept constant, n is kept constant. So F is directly proportional to 1 by root of, here it is L gets cancelled, it is A, in place of A it is area. What is area here? Here also length into breadth. So therefore finally it becomes 1 by 4, F dash becomes 1 by L value increases by 2 times, A value increases by 4 times, this A value increases by 4 times, this D value increases by 2 times. Out of this we get 2 into 2, it is 8 times by 4 times. So 4 is taken to numerator, then we get 1 by 4 times. So 1 by 4 times, that is F naught by 4 times. So therefore frequency becomes F by 2 times. So by increasing all linear dimensions of length, breadth and the distance between the plates of the capacitor by 2 units, by 2 times, not 2 units, by 2 times, then the inductance also change, capacitance value also change. So here by changing all these linear dimensions means length, breadth and distance D, but not number of turns according to given data. So due to that, the frequency changes by 1 by 2 times that of the initial value of the frequency. So answer for this question is, here frequency becomes half, the resonant frequency becomes half. Answer is B for question number 2. So once again, for LC oscillating circuit, the resonant frequency F equal to 1 by 2 pi root L by LC. Here self inductance of the coil is mu naught n square A into L, where small n is number of turns per unit length. So in place of small n, it is replaced as capital N by L. So due to that, here inductance is L equal to, it is mu naught into L square by L square into L gets cancelled. From this mu naught into L square by L into A, into capacitance of the circuit is epsilon naught into A by D, in place of A I write L into B by D. So from this, by increasing, by considering all these linear dimensions by double of its initial values, then frequency becomes 1 by 2 times that of the initial frequency. So here what is our answer for this question? Answer is the resonant frequency of the circuit becomes half of its initial value. So for question number 2, answer is B. Question number 3. A figure shows a cross section of the large section of the infinite metal sheet carrying an electric circuit per unit length. Electric current per unit length is J. A current carrying square loop is placed near the metal sheet such that the plane of the square is perpendicular to the plane of the sheet. Then what we want here? So this is the metal sheet carrying current. So from this to the plane of this metal sheet, here this is the coil is kept. Coil is kept perpendicular to the plane of the metal sheet. So this is the coil carrying current I. So from plane of the metal sheet here, let it carries current I, then magnetic field is into the plane of the paper. So for this sheet here, the magnetic field at this point is here, like this, because current acts out of the plane. For current acts out of the plane here, then it will be into the plane, okay, like this. So this coil is kept like this. So current is into the plane, this coil current is in this direction. By applying Fleming's left hand rule, it experiences force. It experiences force here in one side, At the same time, the other end of this coil experiences force opposite to that one. Suppose the force in this one is supposed to be acts out of the plane. On the other edge, here force will be acts into the plane of the paper. So due to that, these two forces are opposite to each other, they constitute couple. So therefore, net torque acts on this one is not equal to 0, because for this force there is some distance is there. Because it is a small coil, of course, even though it is a small coil, but this distance, this width of the coil is also taken into consideration. But for this vertical edge from this conductor, for this other vertical edge from conductor, there will be slight difference in the distance. So due to that, these forces are not equal. Suppose it is F1, second one is F2. So there will be a net torque acts on the coil. So coil is not in rotational equilibrium. Rotational equilibrium. But net force is 0. So net force is 0, because these two forces, what are the forces here? So if this is very, very small coil, if L and B, if L is for length of B, then F1 is equal to F2. F1 equal to F2, but in opposite direction. Both are equal in magnitude, but in opposite direction. So net force is 0. Both are equal in magnitude, but in opposite direction. So net force is 0. So it is a small coil according to given. See the data. A current carrying square loop is placed nearby the metal sheet. So indirectly, a loop carrying current means it is a small loop here. So due to that, here F1 is equal to F2, equal in magnitude. So therefore, the coil is in translational equilibrium. But not in rotational equilibrium. So net force is 0, net torque on the coil is not equal to 0. So answer for this question, here it is coil, square loop will be repelled away, no, square loop will remains in translational equilibrium. So answer is C for question number 3. So square loop will remain in rotational equilibrium, no, there will be net torque acts on the coil, force multiplied by perpendicular distance, F into this R1 from first edge, R2 to the second edge of the coil. So there will be net torque, it will be different, slight difference in the clockwise and anti-clockwise torques to be observed. For that reason, net torque is not equal to 0. But net force is equal to 0. So coil is said to be in translation equilibrium. Question number 4. In an AC circuit, the instantaneous voltage and current are given as E equal to 5 cos omega t plus root 3 sin omega t volts, and I is equal to here it is, I is equal to sin omega t plus pi by 4. So instantaneous voltage is given as ET is given as 5 into cos omega t plus root 3 sin omega t, and current function is given as IT is equal to sin omega t plus pi by 4. Now what we want? So current leads by a voltage leads by a current by a phase of like this. So you have to calculate phase difference between current and voltage. So first you have to write the equation for V equal to 5 into cos omega t plus root 3 into sin omega t. So you have to convert this one into either single or cosine function. I multiply and divide with 2. 5 by 2 into it is cos omega t into here it is, sorry, I multiplied and divide with root 2 here into 1 by root 2. 1 by root 2 is there, okay. So V equal to here 5 into root 2 into cos omega t into 1 by root 2 plus root of 3 by 2 into sin omega t. So here we can't get here root of 3 by 2 is not in the sin function. So if I multiplied with 2, it is 5 into 2 into cos omega t into 1 by 2 plus root 3 by 2 into sin omega t. then only it is in the form of sin omega t plus cos omega, sin omega t, that plus cos of something plus cos omega t plus sin of something, that is in the form of sin of a plus b. Therefore 10 into it is cos omega t into, here it is sin pi by sin 30 degree pi by 6 plus root 3 by 2, it is root 3 by 2, it is again once again. So cos omega t into sin of pi by 6 1 by 2, and root 3 by 2 can be written as cos of pi by 6 into sin omega t. So it is in the form of sin a cos b plus cos a sin b. So 10 into sin omega t plus pi by 6. So pi by sin 30, pi by 6, sin 30 is 1 by 2. Okay. So pi by 6. So this is the equation for voltage variation accordance with the time, sin omega t plus pi by 6. But the current equation is given here. Current equation is sin of omega t plus pi by 4. Sin of omega t plus pi by 4. So what is the phase difference between these two? The phase difference pi by 6 is less than pi by 4 here. So it is, therefore here it is sin omega t cos b, sin a cos b plus cos a sin b. So it is in the form of sin of a plus b, omega t plus pi by 6. So 10 into sin omega t plus pi by 6. What we want? Phase difference between these two. Delta pi is equal to pi by 4 minus pi by 6. So 6 pi minus 4 pi, 2 pi by 24, that equal to pi by 12. So phase difference between the current and voltage is given as pi by 12. So for current, phase difference is pi by 4. For voltage, phase difference is pi by 6. So these two are having a phase difference of pi by 12 radians. See here, in this case, current leads voltage by pi by 12. Current leads voltage by pi by 12 is the answer for question number 4. See here, if you consider, if you multiply with root 2, your root of 3 by 2, so you can't get this function in single form. For that reason, I considered here it is to be multiplied with 2 and divided with 2. Then only root of 3 by 2 and 1 by 2 can be written as sine and cosine functions, as sine pi by 6 and cos pi by 6. Now it is in the form of sine of a plus b. Okay. So after this, you will get voltage function in terms of time as 10 sin omega t plus pi by 6, and for current function as here already directly it is given as sin of omega t plus pi by 4. By keen observation of these two equations, here the phase of this current little bit more than the phase of the voltage. So phase difference between current over voltage, current over applied voltage is pi by 4 minus pi by 6, that is 2 pi by 24, that is pi by 12. So current leads a phase of pi by 12 over voltage is the answer for question number 4. So answer is D for question number 4. Question number 5. A charged particle enters a uniform magnetic field with the velocity vector making an angle 30 degree with magnetic field. The particle describes a helical trajectory of the pitch. Then the radius of the helix is when charged particle enters, this is the direction of the magnetic field. When charged particle enters at an angle theta with the direction of the magnetic field, then it moves along helical path here. It moves along helical path. The range of this particle is due to horizontal component of velocity. And this here, and this, the radius of this helical path is due to vertical component of velocity of the particle. So range is due to horizontal component of this projection of this particle in the magnetic field at an angle theta with the direction of the magnetic field. So range, this is the helical path, this is the range, and this is the radius of the helical path. So this radius is due to vertical component of velocity, and this range is due to horizontal component of velocity. So range is equal to horizontal component of velocity multiplied by time taken to complete one circular path, that is one spiral path, that is into t. Therefore, v cos theta into t is 2 pi. What is 2 pi r radius by, here it is velocity, vertical component is vy. So, therefore, it is v cos theta into 2 pi r by vy is v sin theta is equal to r. Therefore, v gets cancelled, 2 pi r cot theta is equal to Kepler. So, what we want here? The helical trajectory has pitch is x. So, this range is, this is not a radius, it is range. It is also called as pitch of the helical path, that is given as x equal to 2 pi into, what is the radius here? The radius of the helix that we have to calculate, r into cot of theta value. What is theta value? 30 degree, cot 30 degree. So, from this we want r equal to x by 2 pi into cot 30 degree. Therefore, x by 2 pi into cot 30 is, what is cot 30? Tan 30 1 by root 3 cot 30 root 3, that equal to x by 2 root 3 into pi is the radius of the helical path. Radius of helical path is equal to x by 2 root 3 pi is the answer. So, x by 2 root 3 pi. So, answer is C for question number 5. When charged particle enters at an angle theta with the direction of the magnetic field, this charged particle moves on helical path. So, for this helical path here, so the horizontal range of this particle is due to the horizontal component of velocity, and the radius of this helical path is due to the vertical component of velocity. So, the time taken to complete one rotation by this particle in helical path in the magnetic field is, here this radius of this helical path is due to vertical component of velocity of the projection. So, due to that I consider here the time to complete one rotation by this particle in the magnetic field is, the distance moved for one rotation is 2 pi r by vertical component of velocity as vy. So, 2 pi r by vy is v sin theta. So, here v gets cancelled, it is 2 pi r into cot theta, but this is the range of the helical path that is given in the problem as x. So, 2 pi r into cot 30 degree, from this we can calculate the radius of the helical path as x by 2 pi cot 30 degree, that is x by 2 pi into root 3. So, from this r equal to x by 2 root 3 pi. So, r is the radius of the helical path of the charged particle when it enters at an angle 30 degree with the direction of the magnetic field. So, these are the key points in this question. So, range is due to horizontal component of the velocity of the charged particle enters at an angle other than 90, other than 0 degree. Okay, right. Question number 6. Two small magnetic dipoles with the same magnetic moments mu are located at a distance r from each other. Determine the force of their interaction. So, two bar magnets. And two bar magnets, in place of magnetic dipoles I considered bar magnets, south pole and north pole of the one of the magnet, and its magnetic moment is supposed to be m1, and another bar magnet is kept on the axial line of the first one having magnetic moment m2, and the centers of these two are separated by a distance d. The force of interaction between these two bar magnets of magnetic moments m1 and m2 are separated by a distance d between their centers on same axial line. Then the force of attraction is equal to, here it is, force of attraction is equal to mu naught by 4 pi into, here it is 6 m1 m2 by d to the power 4. In a similar way, when two bar magnets are kept like this, these are the magnetic moments m1 and m2. If the perpendicular distance between their centers is d, south pole, north pole, here south pole and north pole, the perpendicular distance between their centers is here like this. The magnetic moments are like this, the distance is d. If the magnetic moments are like this, the distance between their centers is d, then this is the force of interaction between the two bar magnets. If magnetic moments are kept like this, parallel to each other on their equatorial line, the d is the perpendicular distance between their axis of the bar magnets, then the force of interaction force of interaction is equal to mu naught by 4 pi into 3 m1 m2 by d to the power 4. So this is the derivation after considering of the forces between the south pole and the south pole, north pole and the south pole, and also south pole to north pole and north pole to north pole. So by considering the forces between all four poles of the two bar magnets in the proper direction at proper distances, after calculation of the net and effective force out of all these forces between all four poles of the two bar magnets, after calculation we get this equation as F1 equal to mu naught by 4 pi into 6 m1 m2 by d to the power 4. So what is the force between the two bar magnets placed on same axial line at a distance of separation d? So F is inversely proportional to d power 4. The force in between two pole strength is inversely proportional to d square. Force in between two bar magnets placed on same axial line and d is the distance of separation between their centers. Then the force is inversely proportional to d power 4 and it is 6 m1 m2 by d power 4. So if the d is the distance between the two magnetic moments of the two bar magnets kept parallel to each other, d is the perpendicular distance between their magnetic axes, then there is a force of interaction. Force of attraction or repulsion depends on the arrangement of the poles. So here in this case the force either of attraction or repulsion is given as mu naught by 4 pi into 3 m1 m2 by d power 4. Suppose if these two are n and s, there will be force of attraction minus. If these two are n and n, there will be force of repulsion is plus. So here in between two opposite poles, here we write minus is the force. In between two like poles, we write plus. In second case, here if the in between these two are n and s are there in the same plane, here in the same plane opposite to each other, then there will be force of repulsion. For one magnet n and s, for another magnet s and n is there, then there will be force of attraction. But magnitudes is same, but direction of the net force will be different, reverse. Okay. So on that basis here we take the answer. Now two small magnetic dipoles with the same magnetic moments mu and mu comma mu are located at a distance. So these magnetic moments are along the axis of the two coils carrying currents. Indirectly two small magnetic dipoles. So these are the mu and mu. Okay. So force is equal to mu naught by 4 pi into so these magnetic moments are on the axial line of the two dipoles. Therefore it is m1, that is mu into m2, mu by here d power 4, that is r power 4, but these are axial line, so it is axial line or perpendicular direction, it is 6, it is there, so 6. So therefore from this mu naught by 2 pi into 3 mu square by r power 4. So from this 3 mu naught by 2 pi into mu square by r power 4 is the answer for this question. So for question number 6, answer A, 3 mu naught by 2 pi into mu square by r power 4. The same question I explained in terms of magnetic moments of the two bar magnets are given. Here in this case two small magnetic dipoles are given, the same formula here. There I have taken m1 m2, here it is given as mu1 and mu2, but mu1 equal to mu2. So on that basis these two magnetic moments are on the same axial line. So net force of interaction between these two magnetic dipoles is 3 mu naught by 2 pi into mu square by r power 4 is the answer for question number 6. Right. Next question. Question number 7. Find the current through ammeter A in the circuit shown below. So what is the current enters here at this junction? 10 ampere. So but here 6 ampere leaves out along the other branch. So there must be 4 ampere through this branch. Now at this junction here again it splits as 2 ampere through one of the branch. So there must be 2 ampere in this branch. Okay. So at this junction here it leaves as 8 ampere current. Compulsorily there must be 6 ampere current through ammeter. 6 ampere. So current through ammeter is equal to 6 ampere is the answer for question number 7. So 6 ampere is the answer. Once again, at this junction what the current enters? 10 ampere. So 6 ampere leaves this through this path, so remaining current to pass through this branch only. That current is 10 minus 6, 4 ampere. At this junction again, out of this 4 ampere, there is a deviation of 2 ampere current through this path. So remaining current is to be passed through this branch as 2 ampere. So at this junction, this 2 ampere and current through this ammeter. So ammeter leads the flow of current 8 ampere through this branch. So 2 ampere plus there must be a 6 ampere current flow. So then only it will be 8 ampere through this branch only. So due to that, your current flows through ammeter is 6 ampere by using Kirchhoff's first law of currents. Kirchhoff's current law, according to Kirchhoff's current law, here we calculated current through ammeter as 6 ampere. Question number 8. The period of oscillation of the bar magnet in vibration magnetometer is 2 seconds. T1 equal to 2 seconds. The period of oscillation of the magnet of magnetic moment of inertia, magnet of moment of inertia. The period of oscillation of the magnet of moment of inertia 4 times that of the first magnet. So indirectly here magnetic moment is same. So M1 is equal to M. Moment of inertia I1 is supposed to be I. Now if only moment of inertia becomes 4 times, so time period, what is the time period of the bar magnet in a vibration magnetometer? That is 2 pi into root of I by M into B. So T is directly proportional to root of I. So without changing its mass, without changing its moment of inertia, without changing its magnetic moment, without changing the magnetic field, only moment of inertia is changed by a factor 4 units. Then what happens? It's a time period. So T2 by T1 is equal to root of I2 by I1. So therefore it is root of 4, that is 2. So T2 is equal to 2T1, that is equal to 2 into 2, 4 seconds. 4 seconds is the answer for question number 8. So answer is B. See the meaning of this sentence. The period of oscillation of the magnet of moment of inertia 4 times that of the first magnet. So here without changing magnetic field and without changing magnetic moment of the bar magnet, if only moment of inertia is changed by 4 times of its initial value, then what will be its time period? That is the question. So simply T is directly proportional to root I. So that is T1 by T2 equal to root of I1 by I2. From that I calculated T2 as 4 seconds. So answer for question number 8 is 4 seconds. Question number 9. The magnetic field at the origin due to current element placed at position R bar. Suppose this is an uneven conductor carrying current. Uneven current, magnetic field at origin due to current element placed at the position R bar. So here from this is origin, at this point we want. This is the position vector which makes, this is the current element, this uneven element, uneven conductor carrying current I consider one of the current element DL, IDL bar, IDL. So due to this current element at the position, at the point P with the position vector R bar, the magnetic induction due to this elemental strip is supposed to be dB, then dB bar is equal to, here it is mu naught by 4 pi into IDL bar cross R bar by R cubed. So IDL bar cross R bar by R cubed is the. So this is the equation for question number 9. So answer is, see the options. So always you have to consider it is mu naught by 4 pi into IDL bar cross R bar by R cube. Okay. So answer is IDL bar cross R bar. Yes. Answer is B. For question number 9, answer is B. So the equation for magnetic field at a point due to current element of uneven conductor carrying current I at an angular position pi with respect to the current element is mu naught by 4 pi into ideal bar cross r bar. So, for magnitude it is, for magnitude mod of ideal bar cross r bar, that is ideal into r sin pi, r gets cancelled. So, magnitude of this magnetic field is equal to ideal into sin pi by r square into mu naught by 4 pi. So, mu naught by 4 pi into ideal sin pi by r square is the equation for magnetic field at a point due to the current carrying element of the uneven conductor at one particular point with angular position pi and position vector r bar is ideal sin pi by r square into mu naught by 4 pi r, mu naught by 4 pi into ideal sin pi by r square. In vector form it is dB bar equal to mu naught by 4 pi into ideal bar cross r bar by r cubed is the equation for magnetic induction at a point due to the current element of the uneven conductor carrying current I at a point. Next question. Question number 10. In the series LCR circuit, voltmeter and ammeter readings are. So, voltmeter and ammeter readings are given in the data. See that by keen observation of this circuit here, voltage across inductor is 400 volts and voltage across capacitor is also 400 volts. So, we know that if voltage across inductor is equal to voltage across capacitor, it leads the impedance offered by or reactance offered by inductor is equal to the reactance offered by capacitor, then this LCR series circuit is said to be in resonance. So, LCR series circuit is said to be in resonance. Okay. So, when LCR circuit is in resonance, for LCR circuit, all of you know here, the current becomes maximum and the impedance becomes the resistance used in the LCR series circuit. Therefore, current is equal to peak value of that current, that is maximum value of current equal to voltage applied by the source by impedance. In place of impedance, I replace it as R. Okay. So, V by R. So, what is the voltage applied here? Voltage applied is 100 volt, resistance is 50 ohm. So, V is given as 100 volt and resistance is given as 50 ohm. So, from this, the peak value of current, the maximum value of current in LCR series circuit at resonance is, it is 100 by 50, that equal to 2 ampere is the current that is maximum in LCR circuit when it is in resonance. So, by keen observation of this circuit, the potential drop across inductor is equal to potential drop across capacitor. So, LCR series circuit is said to be in resonance. So, at resonance here we know that current becomes maximum. So, that current is maximum, only we have to consider in place of impedance, we have to consider resistance of the given LCR series circuit only. Therefore, current flows to the circuit is I equal to V by R. So, after calculation we get here the voltage, whatever the voltage here, whatever the voltage applied to the LCR series circuit, that will be the effective voltage of the LCR series circuit across LCR combination when circuit is said to be in resonance. So, therefore, effective voltage is equal to V applied, that equal to V applied is 100 volt. So, answer is here 100 volt and 2 amperes is the voltage, effective voltage to be applied, effective voltage across LCR combination when it is in resonance is 100 volt and current flows at that moment to the LCR series circuit in resonance is 2 ampere, current at that time is 2 amperes. So, answer is C for question number 10. Question number 11. Some magnetic flux is changed from a coil of resistance 10 ohm. As a result, an induced current is developed in it which varies with the time as shown in the figure. then the magnitude of change in flux through the coil in Weber is. So what is the nature of the graph is given here? Nature of the graph is given in between current and time of flow of current through a coil. So here IT graph is given. So IT graph. So what is IT graph? From this graph here it is a straight line which cuts both y axis and x axis. So from this here the area of the IT graph, that will give charge flows to the circuit, charge flows to the coil. So charge is equal to I into dt. So I into dt. So that is I varies in accordance with the time. So due to the I write integral of I dt. I varies in accordance with the time linearly. So therefore, when it is integral of I dt, if coordinates are known to you for the respective graph, then if there is a possibility to calculate area of the given graph, then area of the IT graph that will give charge flows through the coil. So what is the area here? Half into base is 0.1 into height is 4 ampere, that equal to 0.2. Is there any micro value? No, only ampere and time in seconds is given. So 0.1 second it is. So 2 coulombs is the charge flows to the coil. So what is the magnitude of change in flux? So we know that here E equal to d by dt of change in flux. The induced EMF is equal to minus d by dt of flux. So therefore E can be written as I into R. I into R is equal to minus d by dt of flux. In place of I write dq by dt into R is equal to minus, we take magnitude, then it is d pi by dt. So in place of dq I write the total charge flows to the coil. Q by dt gets cancelled. Q by delta t into R is equal to d pi by delta t. Delta t gets cancelled. From this here the change in flux is equal to Q by R. See the data here. I equal to dq by dt into R equal to here d pi by dt it is. Okay. So change in flux is equal to dt gets cancelled, Q into R. So from this what we note here? We calculated charge flows to the coil and resistance of the coil is 10. Okay. So therefore change in flux is 0.2 by 10. So once again see this equation. E equal to V equal to IR dq by dt into R plus equal to d pi by dt. So dt gets cancelled. Q equal to delta pi by R. Yes. Q equal to, so no, it is delta pi is equal to Q into R. Okay. Therefore Q value is 0.2 into R value is 10. That is equal to 0.2 to 2 Weber. So change in flux is 2 Weber is the answer. So for question number 11, answer is A. Very simple calculation it is. So what I did in this problem, IT graph is given. The area of the IT graph that will give charge flows to the coil. When you know charge flows to the coil, you can calculate change in flux through the area of the coil is calculated as delta pi is equal to charge flows to that coil into resistance of the given coil. So I calculated charge flows to the coil from the given graph as 0.2 coulomb multiplied by resistance of the coil is given as 10. Then we get the change of flux through the coil is 2 Weber is the answer for this question. So for question number 11, answer is A. 2 is the answer, 2 Weber. Next question. The magnetic susceptibility of the paramagnetic substance at 73 degrees centigrade is 0.0060. Then its value at minus 173 degrees centigrade. We know that the susceptibility of the magnetic material is inversely proportional to the absolute temperature of the magnetic material. So therefore psi 2 by psi 1 is equal to T1 by T2. So we want psi 2. Psi 2 is equal to psi 1 into T1 by, it is T1 by T2. So what are the values of psi 1? Psi 1 is given as 0.0062. Therefore psi 2 is equal to 0.0060 into T1 value. T1 value is 73 degrees centigrade. 273 plus 73, 273 plus 73, 6, it is 4, it is 346. 346 Kelvin by T2 value minus 173 degrees centigrade. 273 minus 173, that is 273 minus 173, 0, it is 100. So from this do the calculation. After calculation we get the answer as, here it is 0.0120. After do the calculation, after calculation we get 0.0120 is the answer for this question. So it is minus 173, it is 73 degree centigrade. Yes, I think it is also minus 173, it is minus 73 degree centigrade. It is also minus 73. So you correct this one as minus 73 degree centigrade. It is minus 173 degree centigrade. Then only you get it is 200. Then it is 100. So 200 by 200, it is also, it will be different value. So for this one, plus 73 degree centigrade if I consider, and minus 173 degree centigrade as final temperature, then this is the formula value, 0.0060 into 346 by 100. So do the calculation. After calculation we get that is 0.0060 into 3.46. So it is 3 times, here it is 6 into 3, 1.8 or something. So answer is approximately, it is 4 into 624, 2.4. So no option is there, no option is there, all options are wrong, because they have taken it is minus 73 and minus 173. So E, none of the above. Answer is none of the above for question number 12. Okay, I consider it is plus 73 degree centigrade minus 173 degree centigrade. This is the answer. Okay, by after just a rough calculation, it is 3 into 6, 1.8. So here 1.8 nearly it is there, nearly, but it is 4 almost, 2.4 something. So do that, here all options are wrong. So answer is none of the above for this question. Next, question number 13. A non-conducting rod AB of length L has positive linear charge density lambda. The rod is rotated about point A with an angular velocity omega in plane paper. So what is the magnetic moment of the rod? So a rod is under rotation. A rod is under rotation about point A. So it is pivoted point A when it is under rotation with constant angular velocity omega. And this rod is given a charge with a linear charge density lambda. So as we move from center of rotation to the edge here, the speed of the rod is different at different points. So due to that, there may be a magnetic moment, current is different at different points. So due to that, here I consider one of the elemental strip of the rod of length, it is dx, having charge dq, supposed to be at a distance x from center of rotation. Then the velocity of this elemental strip is v equal to x omega. Velocity of this elemental strip is v equal to x omega. Now, what is the magnetic moment due to the rotation of this elemental strip of charge dq in a circular path of radius r? Magnetic moment dm we have to calculate. So dm equal to, due to this rotation of this charge dq in the circular path of radius x, the equivalent current is di into area of cross section. Now I am going to calculate dI. What is dI here? When charge completes one rotation, then its equivalent current is dq by t. What is dq? Charge per unit length is lambda. Lambda into length of the elemental strip is dx by time taken to complete one rotation. When this elemental strip completes one rotation, then only its equivalent current is dI is equal to dq by t. T is, what is t here? 2 pi by omega. So this is the equation for dI, lambda into dx by 2 pi into omega. So substitute equation 2 in 1. Then we get a dm. Dm is equal to, in place of di, I write lambda into dx into omega by 2 pi into, in place of a, area of cross section. Area of cross section of this rotation of the charged particle is pi x square. Pi x square. Okay. So here lambda omega by 2 pi into pi, okay, into x square dx. This is dm. What we want? Magnetic moment due to the rotation of this rod about point A with angular velocity omega. By integrating this one, integral of dm is equal to pi gets cancelled, lambda omega by 2. Lambda omega by 2 into, for x square, integration is integral of x square dx within the limit 0 to L. So from this we get magnetic moment of this rod is equal to lambda omega by, for x square integration is x cubed by 3, 3 into 2 it is 6. And for upper limit, L lower limit is 0, then after substitution of these two limits we get L cubed. So lambda omega by 6 into L cubed is the magnetic moment of the rod under rotation about a point which acts as a pivot point with constant angular velocity omega. So answer is lambda omega by 6 into L cubed is the answer. See here, D is the answer for question number 13. Magnetic moment of the rod is equal to lambda omega by 6 into L cubed is the answer for question number, here it is 13. So is another important and standard model question for JEE mains level examination. Next question, because it is given like this. Okay. So I consider one of the elemental strip at a distance x, having linear velocity v equal to x omega and having charge dq and thickness and width of this elemental strip is dx. From that I calculated di. After that I calculated magnetic moment of that elemental strip. Then by integrating within the limits 0 to L, easily we can obtain the equation for magnetic moment as m equal to lambda omega by 6 into L cubed is the answer for question number 13. Question number 14. A thin rectangular magnet suspended freely has period of oscillation equal to t. For rectangular magnet, time period is t equal to 2 pi root of I by mb. So it is T1. So I1 is equal to I. M1 is equal to M. Okay, now it is broken into two equal halves and one piece is made to oscillate freely in the same field. So when magnet is broken into two equal halves, then here for one piece length becomes, what is the magnetic moment? M dash is equal to 2Lm. Length becomes half. And there is no change in pole strength because pole strength depends on area of cross section. So it broken into two equal halves means only length becomes half. So due to that magnetic moment becomes m by 2. And what happens? It's a moment of inertia. I dash is equal to ml square by 12. Mass becomes half. Length becomes L by 2 whole square by 12. So that means moment of inertia becomes I by 8. So when a bar magnet is broken into two equal pieces, then moment of inertia of the each piece becomes I by 8. Magnetic moment of the each piece becomes m by 2. Now the new time period is t dash is equal to 2 pi into root of I. I is I by 8 by m value m by 2 into b. So, it is 2 is taken to numerator, it is 1 by 2. 1 by 4 it is under root. So, 1 by 2 into 2 pi root of I by mb. So, magnetic moment becomes, time period of oscillation becomes, it is T by 2. See the options here. Now, what is the initial time period T? So, T dash by T we want. So, T dash by T. T dash by T is equal to 1 by 2 is the answer. 1 by 2 is the answer for question number 14. So, when bar magnet is broken into two equal halves, each having half of its original length. So, magnetic moment becomes m by 2. Moment of inertia becomes I by 8. So, time period becomes 2 pi root of I by m into b. I becomes I by 8, m becomes m by 2, 2 is taken to numerator, it is 1 by 4 under root. So, out of root it is 1 by 2. So, it is T. So, that is T by 2. So, T dash by T, that is 1 by 2. What we want? T dash by T, that is 1 by 2 is the answer for question number 14. So, this is a direct question, you can direct question, it is very simple question also. But here calculation of moment of inertia in this problem plays vital role. Okay, right. For question number 14, answer is B. Question number 14, answer is B. Okay, right. Next question. Question number 15. A wire carrying current I is placed inside of a uniform magnetic field B equal to minus B naught K cap. The shape of the wire is parabolic and has equation y equal to 2x minus x square. The force on the wire is, so if any wire carrying current, I is placed in the uniform magnetic field like this, then here we know that the force experienced by this wire is F equal to IL bar cross B bar. This is the equation for the vectorial form of the force experienced by this conducting wire carrying current I placed in the uniform magnetic field like this. What is IL here? IL bar is the shortest length of this wire in the magnetic field. This is L. So on that basis of this point here, now see here what is the length of this wire here. So equation is given at x equal to 0. At x equal to 0 initial point, y is also 0. Okay, at x equal to here it is given as 2 meters it is. So y is equal to 2 into 2x minus x square. By taking 2 as common, x as common factor, it is 2 minus x is equal to y. So therefore 2 minus x is equal to 0 according to given data. So therefore x is equal to 2. So at x equal to 2, y is also 0. At x equal to 2, y is also 0. So this length is 2 meters. Okay, therefore L bar is 2I bar. So L bar is 2I bar is the length of the conductor carrying current kept in a uniform magnetic field directed into the plane of the paper. So therefore F bar is equal to I into L bar cross B bar. I is, what is I here? 4 ampere into L is 2 I bar cross, what is B bar here? B bar is minus B naught K cap. Minus B naught K cap. So that equal to minus, it is I value is given. So I is only I naught it is given. See the data here. Yes, only I is given, not 4 it is. So therefore I into 2I into this is I cap it is, this is current I. So 2I into it is I cap cross B naught into K cap and I put minus outside. That equal to minus 2I into B naught into I cap cross K cap. What is I cap cross K cap? Actually we know that K cap cross I cap is equal to J cap. But here I cap cross K cap is equal to here minus J cap. So minus half minus it is plus. So therefore it is minus half minus it is, what are the options here? So in this case it is 2I bar is there along x direction and B bar is minus B naught K cap and x value is 2, so 2I bar, that is L bar is 2I bar, I values I have taken as it is I. So from this it is F bar is equal to minus 2I into B naught into minus J bar, that equal to 2I B naught into J cap. So what is J cap here? J cap represents the magnitude of the force vector. It is along positive y direction. See the options here. So F equal to 2 B naught I upward. 2 B naught I upward. So upward means this is the J cap representation. So the force experienced by this current carrying conductor in the form of parabolic shape and represented by the function y equal to 2x minus x square. Then here I calculated length of this wire as by keeping or by putting y value as 0 at x equal to 0, and again at this edge of the wire, at this edge of the current carrying conductor, again y becomes 0. So in this equation I substitute again y as 0, then we get 2 minus x equal to 0, that is x equal to 2. That means the length of the conductor, the shortest distance between initial and final edges of the conductor kept in the uniform magnetic field is, here it is IL bar. So I is given as I into L bar is 2I bar. So therefore here it is, after calculation we get this value is I into 2I cap cross minus B naught into K cap. So I cap cross K cap, I cap cross K cap is minus J cap, minus of minus plus J cap we got. So force vector is 2I B naught into J cap. So it acts along positive Y direction. So answer for this one is A. Next, so this is another important model question for JEE mains level. Okay, right. Next question. Question number 16. There is a long cylindrical pipe wire of internal radius R and external radius R carrying current I along its length. The variation of the magnetic field with the distance from the axis of the wire can be represented by. So here it is a long wire carrying current, and this wire is having internal radius R and external one R. Okay, suppose it is having R1 and external radius is R2. So now what we want to see the data here, we want the variation of magnetic field with the distance from axis of the wire can be represented as. So suppose I considered magnetic field induction at a point inside, in between the internal radius and external radius. Here I considered one of the elemental ring of thickness dx dr at a distance r. It lie in between R1 to R2. It lie in between R1 to R2 radius. Then by applying Ampere's circuital law, magnetic induction at this point due to this current carrying element in between inner and outer radius is integral of B into B bar dot dl bar is equal to mu naught into enclosed current in between these 2 points. Enclosed current. So therefore B into integral of dl is 2 pi r. 2 pi r is equal to mu naught into what is the enclosed current? Current per unit cross section, that is I, by current per unit cross section is I by pi into R2 square minus R1 square into area of cross section of this elemental strip, that is pi into, here it is R square minus R1 square. So pi gets cancelled, B equal to mu naught I by 2 pi R into R square minus R1 square by R2 square minus R1 square is the equation for magnetic induction at a point in between internal and external resistance of the long cylindrical conductor carrying current I. So mu naught I by 2 pi R into R square minus R1 square by R2 square minus R1 square. Now here inside, if R is less than R1, B equal to 0. If R lie in between R1 and R2, this is the equation. If R is equal to R2, then we know that the basic equation for magnetic induction at a point on the surface of the conductor of radius R is mu naught I by 2 pi R. Outside point mu naught I by, so R greater than R2, then B equal to mu naught I by 2 pi R. So on that basis, if you plot a graph in between these two, then we get the graph like this. Initially induction is 0 up to here R1. Then afterwards, according to the given equation, according to this equation, B value, as R value increases, B value slightly increases non-linearly. So in between R1 and R2, B value slightly increases non-linearly. So due to that here, this is the non-linearly. After that here, it becomes maximum. After that here, it gradually decreases. So we get rectangular hyperbola. So the variation of magnetic induction in accordance with the radial distance from center to the outside point is like this. So between 0 to R it is, 0 to R it is, there is no magnetic field inside the inner radius. Between inner radius to outer radius, there will be magnetic field. So at the edge of the outer radius here, there B will be maximum. So outside point here, B is inversely proportional to this radial distance. B is inversely proportional to radial distance. So we get the graph like this. So answer is B for question number 16. So this is the equation you have to remember. So magnetic induction at a point here, which is at a distance from the axis of the wire, that can be represented by the equation like this. B equal to B naught I by 2 pi r into r square minus r1 square by r2 square minus r1 square, that is in between inner and outer radius. For inside, for less than capital R1, it is 0. For r more than capital R2, it is mu naught I by 2 pi into small r. So on that sense, we tick the answer for question number 16 as B. So for 16, answer is B. Question number 17. In series LRC AC circuit for a particular value of RLC, the power supplied by the source is P at resonance. So what is power supplied by the source at resonance? That is I square into Z. That the power supplied by the source at resonance is I square into Z, that is I value is I naught. So I naught square into Z. If the value of the inductance is halved, then what is the power of the source that to be supplied at resonance condition? So therefore that is suppose P dash I have written. At that time here I naught square into, in place of Z I write it as R. Okay. So here we know that here at resonance the impedance offered by the circuit is nothing but equal to radius. Nothing but equal to resistance. Therefore P dash is also I naught square into R. So this power by the source, supplied by the source to the LCR series circuit at resonance is independent of the value of inductance. Therefore P equal to P dash. In both cases it is same. Here at resonance Z equal to R is the value at resonance, and current value is same. Current value is same in both cases. In both cases impedance is also same. So due to that, what is the power given by the source to the LCR series circuit at resonance in first case is equal to the power transmitted to the LCR series circuit by the source, that is same. So P equal to P dash. So answer for this question is D. For question number 17, answer is D. Question number 18. A transformer may be used to provide maximum power transfer of two AC circuits that have different impedances Z1 and Z2. So this is a transformer. Okay. So number of turns in the primary coil is N1, number of turns in the secondary coil is N2. The voltage applied here, input voltage is V1, output voltage is V2. We know that in any transformer, the relation between input and output voltages and number of turns in primary and secondary coil is, here it is V directly proportional to N. Therefore V1 by V2 is equal to N1 by N2. Now what we want here, for transformer may be used to provide maximum power transfer. What is power here? Power equal to, in terms of voltage applied, is V square by Z. So here it is for maximum power transfer for both two AC circuits. In both cases power is same. Power is same in both cases. Therefore P is same. So V square is directly proportional to Z. When V square is directly proportional to Z, V1 square by V2 square is equal to Z1 by Z2. In place of V1 square by V2 square, I will write N1 square by N2 square equal to Z1 by Z2. Z1 by Z2. So from this, N1 by N2 is equal to square root of Z1 by Z2. So what is the answer for this one? See here, a transformer may be used to provide maximum power transfer to two AC circuits that have different impedances Z1 and Z2. The ratio of the number of turns needed to meet this condition. So ratio of the number of turns, N1 by N2 equal to root of Z1 by Z2, I calculated. So root of, see here, see the derivation, root of Z1 by Z2. See here, V square directly proportional to Z. So V1 square by V2 square is equal to Z1 by Z2. So from this we get n1 square by n2 square equal to z1 by z2. So n1 by n2 equal to root of z1 by z2 is the answer. So root of z1 by z2, answer is D for question number 18. So here, to provide maximum power transfer to AC circuits, that means a same power is supplied to the two AC circuits having two impedances Z1 and Z2. So we have to consider power is same in both two AC circuits, that we have to assume. On that basis, here I have written the equation V square is directly proportional to Z. Next question. Question number 19. A long solenoid has 1000 turns per meter and carries current of 1 ampere. It has soft iron core of mu r is relative permeability. Relative permeability of the soft iron core is given as 1000. The core is heated beyond the Curie temperature. Beyond the Curie temperature. See the options here. H field, that is intensity of the magnetic field in the solenoid, is unchanged, but the magnetic field B, magnetic field induction B, decreases drastically. The H and B fields in the solenoid are nearly unchanged. The magnetization in the core in reverse direction. So when the soft iron is heated above Curie temperature, then so it turns into a ferromagnetic material. So above Curie temperature, ferro converts into para. So ferro converts into paramagnetic material when it is heated above Curie temperature. So for ferromagnetic materials, here it is given as relative permeability is 1000. So what is the susceptibility here? Susceptibility, what is susceptibility here? It is mu r equal to 1 plus psi. Relative permeability is 1 plus psi. Approximately when this mu r is very, very high, then susceptibility is also in the same ratio. So due to that, here mu r is approximately taken as susceptibility. So for ferromagnetic materials, when they are heated above Curie temperature, it turns into paramagnetic material. For those here the permeability is in the order of 10 to the power minus 5. So that we have to taken from NCERT book. Okay. So for ferromagnetic materials, it is for your ferromagnetic material, it is given as 1000. For paramagnetic materials, this permeability is in the order of 10 to the power minus 5. Okay, from this, what we want? So what we want? See the options H value and B value. In solenoid, a soft iron cylinder is kept like this. Some carries some current I. So in this soft iron cylinder, when it is heated above Curie temperature, in this case, what the magnetic field induction inside of the solenoid, that is mu into H. In place of mu, I write mu naught into mu r into H. So here mu r value decreases. So what is mu r value here? Mu r is directly proportional to psi. So in place of mu r here, in place of mu r, I replaced it as psi. So mu r is replaced it as psi, because here the values are very high. So what is the intensity of magnetization? I equal to psi into H. Intensity of magnetization is I equal to psi into H. So what is H? So what is the magnetic intensity of the magnetic field inside of the solenoid when soft iron core is kept inside of the solenoid is H equal to Ni. H equal to Ni, number of turns per unit length into I. So whatever may be the material is kept inside of the solenoid having either high permeability or low permeability, here it won't affect the value of intensity of the magnetic field. Intensity of the magnetic field cannot be affected by the material that is placed inside of this solenoid carrying current I and having number of turns per unit length as N. But when H is remains same, so H is constant. What we want? B value. So when I equal to psi H, So in this case, intensity of magnetization is directly proportional to psi. So I1 by I2 is equal to psi 1 by psi 2. So I1 by I2 is equal to, in place of psi 1 it is 1000, by psi 2 value I already have given 10 to the power minus 5. So therefore I2 is equal to I1 into 10 to the power minus 8, that is I1 by 10 to the power 8. So that means the intensity of magnetization reduces by 10 to the power 8 times of its initial intensity of magnetization after heating this one above Curie temperature. So this value how to assume? For paramagnetic material, intensity of magnetization is in the order of 10 to the power minus 5. Okay. So therefore intensity of magnetization is reduces by a factor 1 by 10 power 8. See the options here. The intensity of magnetization, nothing but magnetization in the core, increases by a factor. Increases by a factor of 10 power 8, it is wrong. So decreases by a factor. Decreases by a factor 10 power 8. Now the magnetization in the core reverses the direction. No, it only turns from ferromagnetic material into paramagnetic material. So the intensity of magnetization will be in the direction of the external magnetic field. So here in the core reverses direction, it is wrong. The magnetization will be in the direction of the initial magnetic field. So reverses is wrong. Now H and B fields in the solenoid are nearly unchanged. No, H value remains same, B value decreases. H value in the field of the solenoid is unchanged, but B value decreases drastically because, see here, so psi value changes. Psi value changes means here, when psi changes means decreases means mu r decreases. Mu r decreases means B value decreases drastically because mu naught into mu r into H is equal to B. So when mu r value decreases, B value also decreases. So when soft iron core is placed in the solenoid, when it is heated above Curie temperature, then mu r value decreases, due to that susceptibility decreases, due to that B value decreases, but no change in intensity of the magnetic field, that is H. It remains same. But intensity of the magnetic field is different than that of intensity of magnetization. Intensity of magnetization is represented by the symbol I. That equal I equal to psi H. Intensity of the magnetic field is H. And magnetic field induction is B. So B equal to mu H. I equal to psi H. Okay. So that is called intensity of magnetization. So here this, even though it is heated above Curie temperature, it turns into a paramagnetic material. But in paramagnetic material also, magnetization is in the direction of applied external magnetic field. So magnetization will take place in the direction of the applied external magnetic field. So on that sense, we take the answer as A. The H field in the solenoid is unchanged and B field decreases drastically. So for question number 19, answer is A. Question number 20. Figure shows the plot of voltage across the capacitor as a function of driving frequency of the sinusoidal driven electromagnetic oscillator of LCR circuit. So it is a resonance graph in case of LCR series circuit. In resonance graph is plotted in between voltage applied across capacitor and frequency of the LCR circuit divided by when LCR circuit is said to be, this is omega naught. What is omega naught here? Omega naught is the frequency of the source it is. Omega is the frequency of the LCR series circuit. Okay. So for different values of applied operating voltages of AC source in LCR series circuit, here omega value for LCR series circuit, here angular frequency is different for different applied voltages. If graph is plotted between for different applied AC voltages values on y-axis and omega by omega naught values on x-axis. So for different values we get three graphs here. For in case of three cases here, 1, 2, 3, we got three graphs like this. So the sharpness of this graph, see in case of graph 1, the sharpness is more when compared to the sharpness of the graph in 2. At the same time in 3 it is very least. So the sharpness of this V and omega by omega naught graph represents the quality factor. So what is quality factor? Quality factor equal to 1 by, see one, I will check that formula. Quality factor is equal to 1 by R into root of L by C. So the sharpness, if the sharpness is more, quality factor is more. Sharpness is more. So quality factor represents sharpness of this graph. Sharpness is more, here quality factor is more. So if quality factor is more, then it will give lower ranges of frequencies. For any LCR circuit, if you plot a graph in between the applied AC voltage and the value of omega to omega naught ratio, then if any graph is having higher quality factor, then it will give lower ranges of frequencies. If sharpness is more, it will give lower range of frequencies. If sharpness is less, then it will give higher wavelengths of higher ranges of frequencies. So due to that, here in this case, in graph 1 sharpness is more. In graph 2, see the here ABC. Out of ABC, for here C graph, for C graph frequency range is less when compared to frequency range of B, and it is less when compared to frequency range of A. So therefore graph 1 represents C, graph 2 represents B, and graph 3 represents, here it is A. Because if quality factor is high, sharpness is high, due to that here it will give lower ranges of frequencies. So out of all this, here by studying of this one, by studying of these two graphs, for graph 1 sharpness is more, it leads more quality factor, it leads lower range of frequencies of bandwidth. Regarding LCR series circuit, when it is operated at different input AC voltages by AC sources. Okay. So the nature of the graph plotted between operating voltage and omega by omega naught, if it is given like this, then you have to consider the sharpness of the respective graphs. In which case sharpness is more, in that case quality factor of the given LCR series circuit is more. So whenever we use the word quality factor, and it represents sharpness of the given frequency curve. So that quality factor for any LCR series circuit is measured by the relation 1 by R into square root of L by C. So for higher quality factor, inductance should be high, and resistance should be low, and capacitance value should be low. For higher quality factor of the LCR series circuit, for higher sharpness of the LCR series circuit, your inductance value should be as high as possible, and capacitance value should be as low as possible, and resistance should be as low as possible. So then only sharpness will be maximum. At that time the frequency ranges will be lower. Okay, here if sharpness is more for a curve, then frequency ranges will be higher. Wider range of frequencies can be observed in the graph plotted between here, phase difference between these two voltages across inductors and capacitors here, and on x-axis here omega by omega naught values. So this is the graph plotted between phase difference. See the phase difference here, phase difference between voltages and currents in inductor and capacitors. Okay, right. So on that basis we tick the answer. So graph 1 represents graph C. Yes, graph 1 represents graph C. So it is wrong. The circuit of graph 1 is higher quality factor. Yes. Circuit of graph 1, yes. For graph 1, quality factor is high. So it is also correct. So this question is having two answers. Answers B, C. And circuit 3 has having higher quality factor. No. circuitry as having lower quality factor because sharpness is less. So it is wrong. As graph 3 corresponds to graph A. No, graph 3 corresponds to graph C. So on that basis, the answers are B, C, B, C for question number 20. Next question. A uniform magnetic field exists in a space along x-axis, shown in the figure. A rectangular loop of side A and B is rotated in a magnetic field about an axis passing through the midpoint of the side, okay, and parallel to side B. The angular speed omega, which is parallel to the direction B. Then induced current in the loop if resistance of the loop is R1. So this is a coil, this is a coil. Here this is the direction of the magnetic field. When it rotates, these are the lines of magnetic field, magnetic lines of forces, these are. So this is a coil, it rotates like this. So while rotation of this coil, small coil, which is parallel to the direction of the magnetic field, in such a way its bed is parallel. So only it will not cut. No single magnetic line of force will not be cut by the rotation of the edge of this small coil in this direction. So only it will pass through the magnetic lines of forces but not cuts the magnetic lines of forces. Whenever there will be a cutting of magnetic line of forces will take place during the rotation of the coil, then only an EMF is induced. So in this case here, no cutting of magnetic lines of forces according to the given direction, given rotation. So EMF is equal to 0. So induced current, when EMF is equal to 0, then induced current is equal to 0. So answer is C. So during the rotation of this coil kept in such a way, it rotates in the magnetic field and its bed is parallel to the direction of the magnetic field. So due to that, this coil doesn't cut magnetic lines of forces. So due to that, net EMF due to the rotation of the small coil placed in such a way doesn't cut many magnetic lines of forces. Due to that, net EMF is 0. So induced EMF is 0. So induced current is also 0 in the coil. So for question number 21, answer is C. Next, it is another important model question 22. A conducting rod is rotating in a uniform magnetic field perpendicular to it as shown in the figure. See here, see the diagram. The rod is rotating in anti-clockwise direction in the uniform magnetic field directed into the plane of the paper. If the rotation now becomes clockwise with the same angular speed, then what will be the change in potential difference between O and A? O and A is the point here. So this is the conducting rod. When it rotates in anti-clockwise direction, the magnetic field is directed into the plane of the paper. I consider one of the elemental strip of thickness dx at a distance x from center of rotation, and it rotates with linear velocity v is equal to x omega. The linear velocity of this rotating elementary strip is v equal to x omega. What we want here? Induced EMF. So induced EMF equal to, here it is E equal to BLV. B into L is dx into V. That is induced EMF due to this elemental strip. Induced EMF developed between the ends of this elemental strip under rotation in the magnetic field directed into the plane of the paper is BLV. In place of L I have written dx into V. Therefore B into dx into, in place of V I have written, here it is x omega as V. That is induced EMF developed between the ends of the elemental strip under rotation with angular velocity omega. Now, so what is the induced EMF developed between center of rotation to center of this rotating rod to edge of the rotating rod in a magnetic field direct into the plane? That can be obtained by integrating this equation within the limits 0 to L. So B into dx into x omega within the limit 0 to L. So from this, here it is V0 to VA, VA to V0, VA to V0. Okay. So from this it is V0 minus VA is equal to b omega into, for x integration, x square by 2. Therefore, it is b omega into L square by 2. So, it is a potential difference between center of rotation to the edge of the rotating rod in a magnetic field directed into the plane of the paper. That is half b omega L square. If the direction of the rotating rod is reversed, then what will be the magnetic induction? What will be the in potential difference between the center of rotation and this point? So, VO minus VA is equal to simply by reversing its direction of this potentials minus b omega L square by 2. So, now it is to be taken as E1, this one is taken as E2. Now, what we want, see the question, then what will be the change in potential difference between O and A? So, change in potential difference, that is E2 minus E1 is equal to minus b omega L square by 2 minus of this value b omega L square by 2. So, minus b omega L square by 2 minus b omega L square by 2, that equal to minus b omega L square is the potential difference between, change in potential difference in between O and A when the rod is in anti-clockwise rotation and in clockwise rotation. The change in potential difference between center of rotation and edge of the rod in both cases is minus b omega L square is the answer for this question. So, for question number 22, answer is A, minus b omega L square is the answer for question number 22. Question number 23, two long straight parallel wires carrying steady currents I and minus I. These are the two long straight parallel wires carrying currents in opposite direction. I and minus I means both carries current in opposite direction. The distance between the two wires is d. At a certain instant of time, a point charge q is at equidistance from the two wires here, that is at d by 2 and d by 2. Its instantaneous velocity v is perpendicular to the plane. Then the magnitude of the force due to this magnetic fields acting on the charge at that instant. So, these are the two wires. These are the two wires carrying current. One is I, another is I in opposite direction. In between these two wires at equidistance, a charge is there. Then this charge is projected with velocity v. So, due to this current carrying conductor, by applying here right hand thumb rule here, at this point magnetic field is in this direction. Due to this current carrying conductor, here also magnetic field is the same direction. So, here at midpoint of separation of these two conductors carrying current, at midpoint of separation, magnetic field is directed into the plane. So, now in that direction charge is projected, So, when charge is projected in a direction either parallel to the magnetic field or anti-parallel to the direction of the magnetic field, then it experiences no force. So, due to that, here in this case here, so this is the direction of the magnetic field, net magnetic field, it may be 2b and it is currents are I and I. When charge is projected with velocity v in the direction of the magnetic field, then F equal to, what is F here? It is BIL. So, IL bar cross B bar, F equal to IL bar cross B bar. Therefore, that is BIL sin theta. Theta equal to 0. The angle in between velocity vector and the direction of the magnetic field is 0. Therefore, it is 0 because theta equal to 0. So, force is equal to 0. So, what is the force experienced by this charged particle when it is projected at midpoint of separation of these two wires in a plane perpendicular to these two wires is nothing but 0, because here net field is in the direction of the projection of the charged particle. So, angle made by this velocity of this particle and with the net magnetic field is 0. So, BIL sin theta, theta equal to 0. So, force acting on the particle acts on the particle by these two magnetic fields due to this currents in opposite direction is 0. So, for question number 23, answer is 0. So, answer is D. Answer is D for question number 23. It is also another logic and standard question from this chapter. Next question. A thin flexible wire of length capital L is connected to two fixed points and carries current I in the clockwise direction as shown in the figure. When the system is put in a uniform magnetic field of strength B going into the plane of the paper, then wire takes the shape of the circle, then tension in the wire is. So, tension in the wire. So, when wire carries current I kept in the uniform magnetic field, then it attains the circular shape like this. It attains circular shape. So, now what we have to calculate here, see the data, find tension in the wire. When this wire carries current I and placed in the uniform magnetic field directed into the plane of the paper, instead of that irregular shape, it attains circular in shape. When it attains circular in shape, at each and every point tension will be acts radially outwards. I considered one of the elemental strip of length dl with angular width d theta at center. Okay, so I consider this is the elemental strip. For this elemental strip, at this point tension will be T. At this point tension will be T. So, the angular width of this elemental strip is, here it is d theta. So, with respect to midpoint here, if you draw a bisecting line, this angle is d theta by 2. Here also on the other side also it is d theta by 2 at center. Now, the tension in the string acts tangentially at this point of the elemental strip of length dx or dl. So, the force acts radially outward. That is the tension. So, now tell me here along the horizontal direction, here this tension makes an angle d theta by 2. When this angle is d theta by 2, this angle is also d theta by 2. So, the component of tension along vertical direction, that is towards center, is T sine into d theta by 2. Along horizontal direction is T cos d theta by 2. On the other side also it will be T cos d theta by 2. And towards center along radius it is T sine d theta by 2. So, the net force, net tension components towards center along radius of this elemental strip is here T sine theta by 2, that is 2T sine theta by 2, that is d theta by 2 is equal to, here it is force on the elementary strip. Kept in the uniform magnetic field, that is Bi into dl. This is the force acts on the elementary strip, rate acts radially outwards. It was balanced by the sum of the components of tension towards center along radius. So, by integrating this one, 2T into theta is very, very small, d theta is very, very small. So, sine d theta by 2 is written as d theta by 2 is equal to B into I into dl. So, 2 gets cancelled, B into I into dl. What is the length of this elementary? Length of this ring is given as. So, by integrating on both sides, we get integral of Bi into dl equal to integral of 2T into d theta by 2. So, that equal to B into integral of dl. That length of this segment is given as capital L. So, integral of dl is equal to capital L is given in the data. Therefore, it is capital L equal to 2 gets cancelled, T into integral of d theta. Integral of d theta is equal to, it is 2 pi. So, from this we get tension in the string at any point acts in radially outward direction, T equal to BIL by 2 pi. BIL by 2 pi is the equation for tension in the string. Tension in the string acts at each and every point in radially outward direction. So, that value is F equal to BIL by 2 pi is the answer for question number 24. I considered one of the elemental strip having angular width d theta at center and tension acts radially, here radially, tangential direction, tension acts tangential direction on this elemental strip, and the component of this tension of this elemental strip along horizontal direction is T cos d theta by 2, towards center along vertical direction is T sin d theta by 2. we considered components on both sides. The net tension towards center is 2t sin d theta by 2, and these horizontal components can cancel with each other. So now this balanced by the force by this magnetic field on this elementary strip acts in radially outward direction, that is F equal to 2t sin d theta by 2. In place of F I have written BIL, in place of L it is DL. So therefore integral of BI into DL equal to, if d theta by 2 is very small, sin d theta by 2 is d theta by 2. So 2 gets cancelled, t into integral of d theta. Integral of d theta for total circular ring it is 2 pi. For total circular ring, integral of dl is given as capital L. So BIL equal to t into 2 pi. From this, tension at each and every point which acts radially outward direction is given as BIL by 2 pi is the answer for this question number 24. Okay. So answer is BIL by pi. This is the force due to magnetic field. So at this point, tension is BIL by 2 pi is the answer. So answer, where is BIL by 2 pi? It is, yes, answer is C. For question number 24, answer is C. Question number 25. The variation of induced EMF with the time in a coil. If short bar magnet is moved along its axis with constant velocity, is best represented as, when magnet moves towards a coil. When magnet moves towards a coil, we know that magnetic field increases in the area of the coil. So as magnet moves towards coil, here magnetic field increases in the area of the coil. When magnet moves away from the coil, then magnetic field decreases. So what is the equation for? Induced EMF in a coil? E equal to minus E by dt of pi, flux due to magnetic field. If flux varies in accordance with the time in the area of the coil, then only EMF is induced in the coil. Therefore, E is equal to minus d by dt of flux is BA. Here B changes in accordance with the time. So therefore, A is same, minus A into dB by dt. So if B increases, if dB by dt increases, then E is positive. E becomes positive. E becomes here positive multiplied by this negative sign. So E is negative. So when dB by dt increases, E becomes negative. As magnet moves away from the coil, then dB by dt decreases. So due to that, induced EMF will be positive. Minus of minus, dB by dt decrease means minus of minus. So induced EMF will be positive. So as magnet approaches towards coil, induced EMF is negative, and as magnet leaves away from coil, then induced EMF will be positive. So on that sense, see the options here. So here, see, only in the option B there is EMF is negative initially. Only in the option B, induced EMF is negative initially, then afterwards it becomes positive. When compared to all the remaining options, in option B it is negative initially, then induced EMF is positive after some time. So answer for question number 25 is B. Answer is B. For question number 25. Question number 26. So it is not required for JEE mains, right? Question number 27. Two concentric and coplanar circular coils have radii R1 and R2 as shown in the figure. The resistance of the inner coil is R1 and the current in the outer coil is increased from 0 to I. Then total charge circulating in the inner coil. So inner coil radius is R1 and outer coil radius is R2. When compared to R2, R1 is far less. Okay. Now, when current changes from 0 to I in outer coil, the flux through the area of the inner coil will be considered. So if I equal to 0, initial flux is 0 through inner area of the inner coil. When current increases from 0 to I, then flux is equal to pi 2 is equal to magnetic field in the region of the inner coil due to current changes in the outer coil, that equal to B due to outer one multiplied by area of the inner coil. B due to outer one. So for circular coil carrying current I, the magnetic induction at a point near the center, because it is very small area when compared to the radius R2. So due to that, you have to assume magnetic field is uniform in this area. For that reason it is given R1 is far less than R2. Then only you have to write the equation B2 as mu naught into I by 2 into R2 into A1. What is the area of the inner coil? It is pi R1 square. That equal to flux. So when current changes from 0 to I, then change in flux is equal to pi 2 minus pi 1 equal to mu naught I by 2 R2 into pi R1 square. Okay. Now what we want? See the question. Then total charge circulating in the inner coil. We know that change of flux through any coil due to flow of charge is delta pi equal to Q by R. Delta pi equal to delta pi. So total flux through the area of the coil is known to you, that is delta pi. The charge flows through that coil is, suppose it is Q and its resistance is R dash, then the charge flows through that one is equal to 1 by R dash into change in flux through the area of the coil. So 1 by R dash, what is R dash here? According to given data, the resistance of the inner coil is R1 into delta pi. Already we calculated. What is delta pi here? Mu naught I by 2R2, mu naught I by 2R2 into pi R1 square. Mu naught I by 2R2 into pi R1 square. Now what we want here? So flux is BA, mu naught I by 2R2 into area of this one is pi R1 square. So from this R1 gets cancelled. Mu naught I into it is pi is there, pi into R1 by 2R2. Mu naught I into pi into R1 by 2R2 is the equation for charge flows to the inner coil. See the data. Mu naught I into pi R1 by pi R1 gets cancelled. So once again, what is the flux passing through the area of this small coil of radius R1? It is magnetic induction due to the change of current in the outer coil multiplied by area of cross section of the lower one. That is mu naught I by 2R2 is the magnetic induction due to this circular coil carrying current is mu naught I by 2R2. Okay, into the area of cross section of this inner coil is pi R1 square. So therefore mu naught I by 2R2 into pi R1 square is the change of flux passing through the area of the inner coil when current changes from 0 to I in outer coil. Okay. Now what we want? The charge flows through this one. But the charge flows through this one here. Q equal to 1 by R into flux passing through this one. R is the resistance here. What is the resistance of the inner coil? It is 1 by R1 into, what is the flux passing through this one? It is mu naught I by 2R2 into, here it is pi R1 square. So one R1 gets cancelled. So from this Q equal to mu naught into pi I. Mu naught into pi I into R1 by 2R2 is the answer. So for question number here it is 27 answer. Here mu naught into pi R1. Mu naught I into pi R1 into pi is there in the first option. Here so answer, you correct option A as mu naught I R1 into pi by 2R2. Okay. So in all terms pi is missing. So for question number 27 answer is A, mu naught I R1 into pi by 2R2 is the answer for question number 27. Question number 28. A conducting wire bent in the form of parabola y square is equal to 4x carries current I equal to 4 ampere as shown in the figure. The wire is placed in a uniform magnetic field B equal to minus 8 k cap Tesla. It is minus 8 k cap Tesla. Instead of minus 8 k cap, you correct it as plus 8 k cap. That is plus, I correct this numerical value as plus 8 k cap Tesla. Then magnetic force on the wire is, magnetic force on the wire is. Already told, when wire of irregular shape is kept in the magnetic field, then the force experienced by this one, force experienced by this one is equal to IL bar cross V bar, where L is the shortest distance between one end of the wire to another end of the wire. So what is the end of the wire here? So this one is A, this distance is given as 2. So we want, this is 2, but this we want, this distance plus this A to B we want, L is A to B. Here IL bar is I into AB bar cross B bar. So AB bar is the shortest length of the wire placed in the uniform magnetic field. Okay. So now here, how you calculate this one? So when y is given as 4x and x value is given as 2. So y square is equal to 4x. So at x equal to 2 meter is given, then y value is equal to 4 into 2, that equal to 8. So from this y equal to 2 root 2. So this distance is 2 root 2 meters. And this 2 to B also 2 root 2 meter. So what is the distance from A to B? Distance from A to B is 4 root 2 meter. So A to B is directed along negative y-axis according to given data. Therefore it is AB bar is equal to 4 root 2 directed along negative y-axis. So it is minus j cap, and B value is given. So now from this, what is the force acts on the current carrying wire kept in this shape is F bar is equal to I value is 4 into L bar is AB bar, that is 4 root 2 into minus j cap cross, what is B bar here? 8 k cap, that equal to here 4 into 4 16 into 8 128 root 2 into, here it is minus is there, j bar cross k bar I cap, that equal to minus 128 root 2 I cap is the force vector acting on the current carrying wire kept in a uniform magnetic field, directed acts out of the plane of the paper. So for this, here it is, answer is minus 128 root 2 I cap. So for question number 28, answer is minus 128 root 2 I cap is the answer for question number 28. So here what I did in this problem, here I consider the shortest distance between A to B as L bar, IL bar. So I is given as 4 ampere. Okay. Now what is IL bar here? According to given equation, here this value is given as 2 meter. I put x value as 2. Then y square is equal to, here it is 8. So from this y value 2 root 2. So this value is 2 root 2. This value is also 2 root 2. The shortest distance between A to B is 4 root 2 meter along negative y axis. So therefore here the length vector is, current element vector is I dl bar. That is I into dl bar is 4 root 2 minus j k cap. Now force on this conductor carrying current placed in the uniform magnetic field is IL bar cross B bar. So that is 4 root 2 into 4 root 2 into minus j cap cross 8 k cap. So from this, after calculation, we get force vector as minus 128 root 2 I cap is the answer for question number 28. So answer is B for question number 28. Next question. A semicircular current carrying wire having radius capital is placed in xy plane with its center at O, and there is a position x dependent non-uniform magnetic field. So a semicircular clockwise current, you correct this one, a semicircular clockwise current carrying wire has a radius capital is placed in xy plane with its center at origin O, then there is a position x dependent non-uniform magnetic field, that is B equal to B naught x by 2r k cap. So this is the magnetic field which varies in accordance with the position. When we move from origin towards positive along positive x direction, B value increases because x is positive. When we move from origin towards along negative x direction, B value decreases instead of increasing. So it reverses its direction. At the same time, B value decreases. Okay. So here B equal to, what is B value here? B equal to B naught into x by 2r. Depending upon the value of x, then only we consider the direction of B. So if we move from origin towards positive x direction, B is positive. That is acts out of the plane of the paper. When we move from origin towards negative x direction, B is negative. It acts into the plane of the paper. Now on that basis here, so when current flows in clockwise direction, I consider one of the elemental strip like this. This is ideal bar. B here, B acts out of the plane. Okay, B acts out of the plane. What that value here? B equal to B naught x. B naught x by, here it is 2r. B acts out of the plane, that is k cap, because x is positive. I consider one of the elemental strip on this one. I apply Fleming's left hand rule. In this case, elemental strip B acts out of the plane here, and this is like this. B acts out of the plane, and this is elemental strip DL. Current carrying conductor is towards tangential direction. So due to that, the force on this elemental strip is dF, and it is having the component dFy along negative y direction and dFx along negative x direction. Next, so when we move from origin towards negative x direction at any point on this wire here, current like this, we consider the elemental strip like this. Then here on left side here, B is directed into the plane of the paper, that equal to minus B naught x by 2r into k cap. So here x is negative here. X is negative. So B directed into the plane of the paper. B directed into the plane of the paper. So B directed into the plane of the paper, and it is like this. So B directed into the plane of the paper, and the elemental strip carrying current is in this direction. So here the force acts outward. So that is dF. This dF is again classified into two components, that is dFx along negative x direction, dFy along positive y direction. So these components, dFy along positive y direction, dFy along negative y direction, gets cancelled. Only this conducting wire is having net force along negative x direction. So therefore net force is along minus 2Fy. On this elemental strip here, net force is along minus 2Fy. So this elemental strip, this circular wire kept in the uniform magnetic varying magnetic field, when this circular wire carrying clockwise current kept in the varying magnetic field, that is position varying magnetic field, then it experiences force towards negative x direction. So net force is towards, because see here, to Fx, so towards negative x direction. So net force on this current carrying clockwise current carrying wire kept in the magnetic field, which varies in accordance with the position, is having force towards negative x direction. So answer is, see here, the force due to this magnetic field acting on the semicircular wire will be along negative x axis. So for question number 29, so answer is A. So it is one of the important and standard model question for JEE mains level examination. Right. Question number 30. Question number 30. Say a non-conducting ring of radius R has charge Q. A magnetic field is perpendicular to the plane of the ring, changes at a rate. The magnetic field changes at a rate dB by dt. Then torque experienced by the ring. So torque experienced by the ring. So when ring having some charge placed in the time varying magnetic field, it experiences force. Because ring is to be considered as number of elemental strips, I consider on one of the elemental strip the force experienced by this ring elemental strip having charge dq due to the time varying magnetic field is df is equal to BLV, okay, BIL, sorry, BIL. So in place of BIL, it is also replaced by, when time varying magnetic field is there, there will be here induced electric field is developed. So due to that induced electric field on this elemental strip, here the force is E into Q it is, that is dq, E into dq. Now this is induced electric field. How we calculate induced electric field? When time varying magnetic field is there, then induced EMF is equal to minus of d by dt of flux due to magnetic field. That equal to minus d by dt of flux due to magnetic field is BA. Therefore minus A into dB by dt. I consider magnitude. This one has V. V equal to A is pi r square into dB by dt is the induced EMF developed due to time varying magnetic field. So what we want? Electric field intensity, that is induced electric field intensity for the calculation of force experienced by this ring having charge Q and during time varying magnetic field is kept in that region. So therefore, what is induced electric field intensity can be written as the position variation of EMF that will give induced electric field, that is dV by dr, the potential gradient that will give induced electric field, that equal to, by differentiating of this equation with respect to this position, we get 2 pi r into dB by dt, that is constant. So this dV by dr is represented as electric field intensity, that equal to 2 pi r into dB by dt. What we want here? What we want? See the torque experienced by the ring. Therefore torque d toe equal to force multiplied by perpendicular distance. What is dF here? It is E into dq into perpendicular distance. What is E here? 2 pi r into dB by dt into dq into r it is. Therefore it is 2 pi r square dB by dt into dq is equal to torque on small elemental strip. So what is the net torque on the ring? So net torque on the ring is d tau equal to 2 pi r square into dB by dt into integral of dq. Therefore net torque on the ring is equal to 2 pi r square dB by dt into q, 0 to q. Charge given to the ring as q. So therefore 2 pi r square q into dB by dt is the net torque acts on the ring when charge distributed on this one is q. Charge distributed on this one is q. So answer for this question is 2 pi r square q into dB by dt. So what I considered on the elemental strip of this ring of charge dq, and it is supposed to be in the electric field intensity produced due to time varying magnetic field. All of you know, when time varying magnetic field is created, due to that induced electric field is formed. In that induced electric field, it experiences force dF for an elementary strip of the ring having charge dq. Now I calculated induced EMF due to time varying magnetic field as E equal to minus A into dB by dt. In place of A for ring it is pi r square into dB by dt. So when you know potential difference between the edges of this ring here. By differentiating this equation with respect to this distance from center to this point here, we get 2 pi r into dB by dt. That will give induced electric field intensity in the region of the ring due to time varying magnetic field. Now you replace E as 2 pi r into dB by dt into dq. But we want the torque experienced by the ring. Torque is equal to that force multiplied by perpendicular distance, that is df into r. That force is E into dq into r. So E value is 2 pi r into dB by dt into dq into r. So by integrating on both sides, we get torque experienced by this ring when it is placed in a time varying magnetic field is written as 2 pi r square into q into dB by dt is the answer. So for this question number 30, answer is D. So this is the explanation for questions relates to electromagnetic induction, AC, and also magnetism and matter. So out of all these 30 questions, there are 18 most important questions are there under explanation. So go through this all these questions, and these are most valuable and important questions regarding final JEE mains level examination. Okay, thanks to all. Please subscribe this channel for next future videos. Okay, thank you all.